So it's joint work with Eleonora Romano. So she was a former PhD student of mine, and now she works in Genova. Okay. And so I want to talk about the classification result of some Fano fourfolds. And I will start with a brief introduction on Fano varieties, and we work over C. So X. So I will only consider smooth Fano varieties in this talk. Okay, so we know that there are finitely many families in each dimension. Okay, and they are classified up to dimension 3. Okay, so in dimension 1, we only have P1. In dimension 2, we have the pets surfaces. And even if I think all people here are experts, I will still recall that they are P2, P1 cross P1, and the blow-ups of P2 in up to 8 general points. And in dimension 3, as we heard already yesterday from Vanya, we have 105 families of Fano threefolds. Okay, and starting from dimension 4, we do not have a complete classification. And I want to recall some numerical invariants of X. So first of all, let me recall that N1 of X is the vector space. So usually this works. I hope it will work. Is a vector space of 1 cycles in X with real coefficients up to numerical equivalence. Okay, and okay, let's do this, maybe it's better. And so this is a real vector space of dimension rho X, which is the Picard number of X. Okay, and since X is Fano, if you use the exponential sequence and vanishing, you see that actually the Picard number is just the second Betti number. And so the Picard number is at most 9 for the pezzo surfaces. And the Picard number is at most 10 for Fano threefolds. Okay, and then I want to introduce another invariant, which is the Lefschetz defect. Which is defined as follows. I start with a prime divisor D in X. Okay, and I want to compare N1 of D with N1 of X. Okay, so we take the inclusion of D in X, and I gives a natural push forward from n1 of d to n1 of x, which takes the class of a curve in D and sends it to the class of the same curve in X. And I'm interested in the image of this map, which I denote by n1 of dx. Okay, so this is just the subspace of n1 of x spanned by classes of curves in D. Okay, and I'm interested, in fact, not only in the not in the subspace, but in the possible codimension of this linear subspace. Okay, which can vary from 0 when n1 of dx is a whole n1 of x up to the Picard number of x minus 1. This is because, of course, n1 of d, I mean, the image of n1 of d is always non-zero, because if you take a curve in D, its image will be a non-zero class. Okay, so n1 of dx is always non-zero. Yes, and also we have a dual description. So we can consider an upper one of x, which is a vector space of Cartier divisors with real coefficients up to numerical equivalence again, and also an upper one of D, and we have the restriction here, and this is isomorphic to the second real cohomology group of X, and this is included in the second real cohomology group of D, and here we have the restriction at the level of cohomology. Okay, and so the codimension of n1 of dx is just the dimension of the kernel of R, and so it's also the dimension of the kernel of R tilde. Okay, so somehow maybe it's more natural to see this number as at the level of the restriction at between the second cohomology groups. On the other hand, the way to work with it is really as with one cycles. And also, I want to note that if the dimension is at least 3 and D is ample, then n1 of dx is the whole n1 of x by Lefschetz, by Lefschetz theorem on hyperplane sections. Okay. Okay, then let's define the Lefschetz defect. Delta is a maximum of all the possible codimensions of n1 of dx, where D varies among all prime divisors in X. Okay, so I'm not assuming anything on the singularities, I'm just looking at codimension 1 subvarieties. Okay, so we can say that delta varies between 0 and the Picard number of x minus 1. So here you can see that this construction is interesting when the Picard number of x is bigger than 1. Okay, so for Fano varieties of Picard number 1, this construction is just useless. So we are thinking of studying Fano varieties with Picard number bigger than 1. And so as you see, at least starting from dimension 3, this number measures the failure of this instance of Lefschetz theorem for non-ample divisors. Okay, so when delta is bigger than 0, basically you have to think that it means that X contains some prime divisor with a Picard number smaller than the Picard number of X, more or less. Okay, then what's the property, the important property of this invariant? It is that if delta is at least 4, then X is a product of a surface with another Fano manifold. Okay, and then we have a weaker statement when the Lefschetz defect is 3. So then there is, so basically if delta is 3, we have on X a fibration in the pezzo surfaces. So there exists F from X to T, where so T is smooth, Fano, and the difference of the dimensions is 2. And the difference of the Picard numbers is 4. So rho X minus rho T is equal 4. And F is an equidimensional. F is an equidimensional contraction. Okay, and I will denote by capital F. So let me write, and the general fiber F of small f is a del pezzo surface, of course a smooth del pezzo surface with Picard number at least 4. Okay, so when the Lefschetz defect is 3, we still have a structure theorem with a fibration in the pezzo surface where the target is smooth and Fano. Okay, so this is in general, and now we go to the case where X is a fourfold. So from now on we consider Fano fourfolds. Okay, and so if delta is at least 4, then by the theorem you see that X must be a product of the pezzo surfaces. And so that's fine, we know this Fano fourfolds, okay? So we can reduce to study Fano fourfolds with Lefschetz defect between 0 and 3. Okay, so the project that I want to talk about that we have with Eleonora is the classification of the case with Lefschetz defect 3. Okay, so from this point of view, this is the simplest case. Okay, so project, we have, we would like to have a classification. Okay, now let's assume that we have a Fano fourfold with Lefschetz defect 3. And let's see what we can say. So from the theorem that I stated before, okay, we still have this fibration, and now also T is a del pezzo surface, okay. So we have F from X to T, where T is a del pezzo surface, and the difference of the Picard numbers is 4, okay. Now I want to explain a little argument also to give an idea of how one uses this Lefschetz defect in practice. So we take, let us take a prime divisor D in X whose image in T is a curve. So let D in X be a prime divisor such that f of D is a curve C. Okay, and then if we have gamma in D an irreducible curve, the image of gamma, there are not many possibilities, is either a point or the curve C. Okay, then I want to consider the push forward of one cycles associated to F between N1 of X and N1 of T. Okay, and of course this is a surjective linear map, and the dimension of the kernel is 4 because it's the difference of the Picard numbers. Okay, and inside here I have this linear subspace, which, remember, it was the linear span of the classes of curves in D, so the classes of these gammas. And then if I do the push forward of the class of gamma, I get either 0 if the image was a point, or a multiple of the class of C if the image is C, so it belongs to the line spanned by the class of C inside N1 of T. Okay, so we can say that the image of N1 of dx is just a line. Okay, and then by using linear algebra, we know that the dimension of N1 of dx is at most 1 plus the dimension of the kernel, which was 4. So we get that the dimension is at most 5. Okay, so typically we can use the Lefschetz defect when a geometrical situation gives us a divisor with small dimension of N1 of dx, or with small Picard number, like here. So this contraction F gives us a divisor, I mean the situation gives us a divisor where the dimension of N1 of dx is at most 5, okay? And then we know that delta was 3 by assumption, but this was the maximal codimension of N1 of dx, okay? And this is bigger or equal than rho minus 5, and so we deduce that rho is at most 8, okay? So we see that Fano fourfolds with Lefschetz defect equal 3 have Picard number at most 8. And then, so maybe let me highlight this. And then by applying an old result of mine, one can show that if actually the Picard number is 7 or 8, then X is a product. Okay, and then here, so F, which was a fiber, is just the del pezzo surface with Picard number 4. So it's the blow up of P2 in 3 non-collinear points. okay? And T is the Lefschetz surface with Picard number 3 or 4, depending whether the Picard number of X is 7 or 8. And also, in this case, F is just the projection. Okay. And so in particular, it is smooth. And I want to note also that in this case, these two Lefschetz surfaces, T and F, are toric. So in fact, this X is toric. Okay. So for Picard numbers 7 and 8, we have only these two cases of Fano fourfolds with Lefschetz defect 3. They are products and they are toric. Okay. So basically we can assume now that the Picard number is at most 6. Okay. To study Fano fourfold with Lefschetz defect 3. On the other hand, remember I had that the difference of rho x and rho t is 4, and t is a surface, so rho t is positive, so the Picard number of x is at least 5. Okay, so in the end, rho x, the possibilities that we have to study are just these two. Okay, so where the Picard number of x is 5 or 6. Okay, so our result that I want to explain today is the classification of the case of Picard number 5. Okay, so the classification of Fano fourfolds with delta equal 3 and rho equal 5. So let me give off a statement. So there are 6 families of Fano fourfolds with Picard number 5 and Lefschetz defect 3. And so 4 are toric. So in particular, toric Fano fourfolds are rigid. So these are just, I mean, in each case, it's one fourfold. It's not really a family. And 2 are not toric. And one of these is a new example. And has non-trivial deformations. So it's actually a family. And also all 6 are rational. Okay. Okay, so in the rest of the talk, I want to explain the strategy to prove the theorem, and also I want to explain what are these two families, non-toric families, and so let me also say that we have a project or work in progress, something in between, to get a similar classification for the case of Picard number 6. Okay, so we think that with similar techniques, it should be possible to get a similar classification also for the other case, so to get a complete classification of Fano fourfolds with delta equal 3. Maybe I will say something more on the case of Picard number 6 at the end. So maybe this is a good time if there are questions. No? Okay. Okay, so our starting point for the strategy of the proof is this morphism that I already introduced this fibration in the pezzo surfaces. So here we have rho x equal 5, and the difference of the Picard numbers was 4. So rho t is 1, and t is a smoothed pezzo surface. So t is P2. Okay. And so what happens is that the proof of the theorem that I stated at the beginning on the Lefschetz defect, for the case delta equal 3, not only it gives this fibration, but also somehow the proof gives an explicit factorization of f as a sequence of elementary contractions. Okay, so I will explain this factorization. So we have a factorization. Of f as follows. Okay, so this is f. Okay, so let's see what are the intermediate steps. So this is a P1 bundle. So Y is a smooth threefold. And the second map is again a P1 bundle. So X2 is a smooth fourfold. Okay. And then the last step is birational. So now if you count the Picard numbers, we have 1 on P2, 2 for Y, 3 for X2, and 5 for X. So this step from X to X2, the increase is 2. And in fact, this last step is the blow up of two disjoint smooth irreducible surfaces. B1, B2 in X2, which are finite over P2 under the map from X2 to P2. Okay. Okay, so I want to always, in all this construction, I want to keep in mind fiber-wise what happens. So remember that capital F in X okay, is a general fiber of the map. Okay, so this factorization fiber-wise gives, I mean, the general fiber of X2 over P2 will be a Hirzebruch surface, okay, because it's a P1 bundle over P1. And then we blow up this Hirzebruch surface in finitely many points, which will be given by the general, I mean, the degrees, the number of the points will be the sum of the degrees of B1 and B2 over P2, okay? And then we get F, which is del pezzo, okay, because X is Fano. So a posteriori, we deduce that the general fiber of X2 over P2 is also del pezzo surface. So it's either P1 cross P1 or the Hirzebruch surface F1, okay? And then we also, so there is a work by Pedro Montero and Eleonora where they also use this diagram. So they do a technical analysis. So let me just write technical analysis of this diagram. So they have a number of technical results that I will not mention because, I mean, they're actually technical. So for instance, we know the possibilities for Y here. But I will just mention one which is easy to explain and which is also essential. Basically, they show that for these two surfaces, B1 and B2, that we blow up from X2 to X, at least one of the two must be a section over P2. So it must have degree 1 over P2. Okay, so we can assume that it is B2. So they show that B2 must be a section over P2. Okay, and then this makes things simpler. Okay, now I want to distinguish the two blow-ups. So we get a more detailed diagram. Okay, and then I want to first blow up the section. And then I blow up the transform of B1, which may have some degree bigger than 1 over, no, this is not P1, it's P2. Okay, blow up of the transform of B1, and this is a 2. Okay. Okay, now when I look at this diagram, I see that, I mean, from Y to P2, this is a P1 bundle, so it is smooth. And from X2 to Y, it is also smooth because it's a P1 bundle, so this composition is smooth. Okay. And then since we are blowing up a section, also this composition here, it's again smooth, of relative Picard number 3. Number 3. And I mean, it's also K negative. Okay. And so the fiber, every fiber of X1 to P2 is isomorphic to the del pezzo surface with Picard number 3, so it's the blow up of P2 in 2 points. Okay, and now we use this to get another factorization of this map. So maybe it's good to think of this fiber-wise. So let me recall, like the students in algebraic geometry learn, when you blow up a P2 at 2 points, you have 3 minus 1 curves, and depending how you contract, you get to different surfaces. Okay, so if you want to get to P2 in a birational way, you have to contract the 2 external minus 2 curves. Okay, instead, if you contract the central one, you go to P1 cross P1. Okay, and here you see from X1 we contract 1 minus 1 curve, and then we choose, instead of the birational map, we choose a P1 bundle and go to Y. Okay, so we basically want to change this. Okay, so basically, we show that up to possibly changing the factorization of F, we have the same steps as before. But then from X2, instead of choosing the P1 bundle, we can also choose a birational map and go to Z, and Z is a P2 bundle over P2. Okay, so Z is of course a smooth fourfold. Okay, and then the composition of X to Z is the blow up of three surfaces, pairwise disjoint, smooth, irreducible surfaces, say S1, S2, S3 in Z, okay? And so in the ordering of the blow-ups, here is the blow-up of S3, and this is the blow-up of S2, and this, the last one, is the blow-up of S1, okay? And S2 and S3 are sections, okay, while S1 has finite degree D over P2. Okay. So let me again draw a picture of what happens fiber-wise. We have ZP, a general fiber of the P2 bundle. Okay, and in this P2, we have some special points. We have one point which is in S2, in the section S2, one point which is in the section S3, and then we have these D points D points in S1, okay? So our surface F, the general fiber of the morphism from X to P2 is a blow up of these points. Okay, and since F was del pezzo, we conclude that D is at most 6, and moreover, all these points are in general linear positions. General. Okay. And now, so the first case, the easy case, is when also S1 is a section. So when D is 1. So this is easy case. So this is easy because we have that Z is a P2 bundle over P2, so it's the projectivization over P2 over rank 3 vector bundle. Okay, and we have this S1, S2, S3. They are pairwise disjoint sections. And also they are fiber-wise non-collinear, because we know that these points are in general linear positions. Okay, and then it's easy to see that this implies that a vector bundle splits as a direct sum of line bundles. Where each Li, I mean Si as a section corresponds to the projection of E onto Li in this direct sum, okay? But then Z is a projectivization of a decomposable vector bundle on P2, so Z is toric. And also Si, since it's given by the direct summons, I mean the sections are given by the direct summons of the vector bundle, so this means that the surfaces Si are torus invariant. And so X is obtained from a toric variety by a blow-up of some torus invariant subvarieties, so X is toric too. And then it's easy because toric Fano fourfolds are classified. Oop. By Batirev in 1999, plus Sato, who had the missing one year later. And it's easy to see it's easy to see the Lefschetz defect. And so you just go and check, and you see that there are 4 possibilities for X. In these cases, in this case, F is smooth, F from X to P2, and the fiber F is just the blow up of P2 at 3 points, non-collinear, and one of these possibilities is just the product. One is P2 times F, and the other ones are not products. Let me see. Okay, so this is what happens when the degree of the last surface S1 that we blow up is 1, X is toric, and then it's an easy case. So let me instead talk about the case where D is bigger than 1. Okay. So this is actually the technical part of our work, to study this case, and I will not enter in the details. So I will just say what we do, but I will not explain how. What we do is we construct, in this case, a prime divisor H in Z, which is a P1 bundle over P2. So I mean that fiber-wise H is really a line, and H contains the surface S1. Okay, so I would say this sentence is the part where we have to work. But then once we have this, it's easy to conclude what the degree must be, because remember we had our P2 with the 2 points S2 in S2 and S3. And then here we have a line, which is H intersected with the fiber. And we have the D points in the line. Okay. But we knew that since the blow up must be del pezzo, so these points are in general linear positions. So basically we get that the D points in S1 are collinear and in general linear position. And so we get these two. Okay, so basically the degree of S1 is either 1 or 2. And then once we know that the degree is 2, it is not difficult to conclude. And basically we see that there are two possibilities for Z. So one is the projectivization over P2 of O plus O plus O of 1, and the other one is the projectivization over P2 of O plus O plus O of 2. Okay, and basically this Z determines, once we know that the degree is 2, determines the two different families that I mentioned in the statement. Okay, and yes, before describing the two families, I want to point out that so somehow this gives two possibilities for X, and in both cases F from X to P2 is not smooth, because of course when we blow up, at the points of P2 where the morphism from S1 to P2 ramifies, then we get a singular surface. And the general fiber F has Picard number 5. So it's the blow up of P2 in 4 points instead of 3. Okay, now I want to describe, yes, in these 10 minutes I want to just describe the two families. So the first case where Z is this variety, this is just the blow up of P4 at a line. Okay, so we have Z, this is a P2 bundle, and this is the blow up at a line. Okay, and then we have the exceptional divisor D of the blow up. Okay, so D is isomorphic to P1 cross P2. Okay, and so S2 and S3, so of course to describe X I have to tell you what are the three surfaces that we blow up from Z. S2 and S3 in D are fibers of the blow up. in the exceptional divisor. So they are isomorphic to P2. That, I mean, they always are isomorphic to P2 because they are sections, okay? And S1 in Z is the transform of a general quadric. From P4. So S1 is P1 cross P1. Okay. And in this example is again rigid, and it was already known. It has been described by Tsukioka, Toru Tsukioka. And in fact, it's you can do this example in any dimension, not only in dimension 4. Okay, this was the first case. Let's go to the second case. In fact, it's similar because in this case, Z again, Z has the P2 bundle, but also an elementary divisorial contraction, similarly to the blow-up of the line, because Z is a resolution of the weighted projective space P of 1, 1, 1, 2, 2, which can be seen in P7. Is the cone over the Veronese surface. Oh. Today my tablet is unhappy. Over the Veronese surface in P5 with vertex align. Okay, so we have a similar picture as before. So we have Z has the P2 bundle and this elementary divisorial contraction to W. So let's just write birational. Okay, and this there is an exceptional divisor D. Which is sent to the vertex of the cone, and D is again isomorphic to P1 cross P2, and again S2 and S3 are contained in D and are fibers of the birational map. Okay. Up. And then what is S1, which is the most interesting of the three surfaces? S1 in Z is the transform of a general section W intersected with a hyperplane and with a quadric in P7. And one can check that S1 is a del pezzo of degree 2. Okay. And this gives a deformation family for X because we compute that H1 of Tx is at least 6. So somehow when we saw that S1 is a del pezzo surface of degree 2, this makes you think about a family because S1 has moduli. So we compute the Euler characteristic of the tangent sheaf using Riemann-Roch, and this gives us an estimate on H1 of Tx. Okay, and yes, so this family is a new example. So for this reason, we have to actually show that this construction gives a Fano fourfold. So there is some computation to show that when you start from this Z and blow up these three surfaces, you get a Fano fourfold with Lefschetz defect 3. Okay, so maybe I would just conclude by saying something on the case of Picard number 6. I said we have this project work in progress on the last case. So we expect that it should be possible to get a similar classification. So on one hand, in principle, the case of Picard number 6 should be easier because the bigger the Picard number, the more rigid is the situation, okay? On the other hand, we want to use the same technique, so to use this vibration onto T, but onto the surface T, but in this case the base will not be P2, but it will be either P1 cross P1 or the Hirzebruch surface F1. So in principle that this gives more cases to consider, so we still don't know. And of course, it will be interesting if also in the case of Picard number 6, we find some non-toric families, some new examples, but we still don't know. Okay, I think I will stop here.